Today, we're going after a ghost in the machine. That invisible echo that can mess with everything from your Wi-Fi to your phone calls. We're talking about something called inter-symbol interference. You know that feeling, right? You're in the middle of a huge download, or maybe you're streaming the season finale, and suddenly, everything just grinds to a halt. You're left wondering why your Wi-Fi is crawling when you've got full bars. And our first instinct is always to blame the signal strength. We get closer to the router, maybe we restart it, but a lot of the time, the problem has nothing to do with how strong the signal is. It's all about how clean it is. The real culprit is actually way more interesting. Imagine you're writing a message in the sand right at the edge of the water. If the waves come in just a little too fast, the letters start to blur and wash into each other until you can't read the message anymore. Well, that's pretty much what's happening to our data. So to really understand how this blurring happens, we need to follow a single bit of data on its journey, from the second it's created to the moment it arrives at its destination. Every little piece of digital information goes on this adventure. It starts as a basic concept, our input bits, ones and zeros. A transmitter then turns those bits into a wave. That wave travels through a channel. That could be the air around us or a physical cable. And on the other hand, a receiver has to listen in and make a final call. What was the original message? But here's the thing, that journey is almost never perfect. And when things go wrong, we run smack into our problem, interference. This is where the signals start to get really messy. And this mess has a name, inter-symbol interference, or ISI for short. It's basically a type of distortion where one symbol, or one piece of data, starts to interfere with the ones right after it. You can think of it like someone talking so fast that their words just start to slur together. The end of one word just bleeds right into the beginning of the next. See, in a perfect world, our digital signals would be these nice, clean, separate pulses, super easy to tell apart. But in the real world, the channel they travel through causes them to spread out and lose their sharp edges. They start overlapping, making it incredibly hard for the receiver to figure out where one bit ends and the next one begins. And the source material really nails the definition here. It calls ISI the residual effect of other transmitted bits on the decoding of the current bit. It's that leftover energy, the echo of a signal that's already passed, that messes up what's happening right now. So how does this all work on a technical level? Let's take a look at the anatomy of a corrupted signal by breaking down the math behind it. And don't worry, it's actually way simpler than it sounds. It all boils down to this one simple but really important equation. The signal your phone or computer actually gets isn't pure. It's a combination of the signal you want, plus those echoes from other signals, and a little bit of random static on top. So first we have our hero, the desired signal. At any single moment, this is the one specific bit, that one or that zero, that we're trying to read. It's the pure intended piece of information. And then, of course, you've got the villain, the ISI effect. This is the ghost of the signals that came just before. Their energy hasn't completely faded away, so it lingers and corrupts our hero, making it way harder to identify. And finally, you just have random chaos. Think of this as the background static you hear on a radio or trying to have a conversation on a windy day. It's all the unpredictable noise from the world around us that gets mixed in, adding yet another layer of confusion. Okay, so if the signal we get is a mix of a hero, a villain, and just plain chaos, what's the goal? Well, the goal is perfect clarity. Let's imagine what an ideal, interference-free world would look like. To get this perfect clarity, two things would have to happen. First, you'd have to completely eliminate all inter-symbol interference. No echoes whatsoever. Second, you'd have to get rid of all the random noise, creating a perfectly silent channel. Only then could our hero signal arrive completely untouched. And just look at the difference that makes. On the left, you have our messy reality. But when you get rid of the ISI villain and the random noise, the equation becomes beautifully simple. The output is just a direct, predictable result of the input. What that really means is, in a perfect system, the signal you receive is a flawless, crystal clear copy of what was sent. We could rebuild the original data with zero mistakes. Every single file would download perfectly, every video would stream without a single glitch. And that brings us to the big final question. If we know what perfection looks like, why can't we just do it all the time? Well, the answer comes down to a fundamental trade-off. To send data faster, we have to pack our signals closer and closer together. But the closer they get, the more they create those echoes that interfere with each other. So the very thing we do to get more speed is what creates the interference that slows us down. And solving that paradox, well, that's the constant battle at the heart of all modern communication.